Okay, so in the last video, I introduced this concept of formal charge, and I told you that it was a way that we were going to be able to determine the best lowest structure when there are multiple structures that exist. So now I'm going to show you an example of how to do that. So the first things you need to know are the rules for choosing the best structure. So first of all, the best structure has the fewest atoms with formal charge on them. You'll see what I mean in a moment. And furthermore, the best structure has the negative formal charges on the most electronegative atoms. So these are kind of some rules that we're going to go back to when we're looking at these resonance structures. So I have drawn here two resonance structures for this molecule. So you can see that this lone pair of electrons exists on either the nitrogen or the carbon, and furthermore they have different connectivity. So this hydrogen is either attached to the carbon or the nitrogen. So you could equally as well draw both of these Lewis structures, but we want to know which one is the best Lewis structure. So the way to do that, we're going to determine the formal charge on each one of these atoms and then apply our rules up here to see what we come up with. So remember, the way to assign formal charge is to count the valence electrons and then subtract the non-bonded electrons plus 1/2 of the bonded electrons. So let's do that first for this molecule over here on the left. So we know the number of valence electrons for hydrogen to be 1. We know the number of valence electrons for carbon is 4, and we know the number for nitrogen is 5. And this is straight from the periodic table, or the electron configuration. Now we'll look at the structure and find the number of non-bonded electrons. So here for hydrogen you can see it's 0. For carbon it looks like we also have 0. And for nitrogen we have these 2 here. And then finally let's look at the bonded electrons. So for hydrogen we have 2. For carbon we have 8. So it's all filled up. And then nitrogen has 6. So if we evaluate the formal charge using these values, so we're going to do 1 minus 0 plus 1/2 times 2, so it's 1 minus 1, basically. So the formal charge on that hydrogen is 0. Similar for the carbon, we'll do 4 minus 0 minus 1/2 of 8, which is 4. So it's 4 minus 4, that also gives us 0. And then finally we have 5 minus 2, so that gives us 3, and then, hold on a sec, yeah, so 3, and then minus another 3, so that also gives us 0. So there's a 0 formal charge on each one of these atoms, and the sum of the formal charges equals to 0, as it should, because this is a neutral molecule. Let's do the same thing for this guy, and see if we find something similar. So once again, we know the valence electrons from the periodic table. So we just have to look at the structure and figure out the number of bonding and non-bonding electrons. So for hydrogen, once again, we have 0 non-bonded. For nitrogen, we also have 0. And for carbon, we have 2 this time. The number of bonded electrons, on the other hand, is 2, 8, and 6. And the formal charge we calculate with this expression once again. So for hydrogen, this is once again going to be 0, same as last time. But this time we're going to see that the nitrogen and the carbon are going to have a non-zero formal charge. So if we do 5 minus 1/2 of 8, which is 4, we end up with plus 1 on the nitrogen. And in this case, we have 4 minus 2, which gives 2, minus 1/2 of 6, which gives minus 1 in that case. Okay, so now we have the formal charges on each one of these atoms for both of these structures, and we can go back to our rules. So, as I've alluded to, the best structure is the one that has the fewest atoms with formal charge. So that gives us an indication that this structure on the left is a little bit better. Furthermore, the negative formal charges should exist on the most electronegative atoms. So in this structure, where we actually have a negative formal charge, it doesn't exist on the most electronegative atom. We know from the periodic table, nitrogen is more electronegative than carbon. So if this structure were to be stable, the nitrogen should be the one carrying the negative charge, and that's not the case. So that's further proof that this structure on the left is the more stable one. In the next video, we're going to look at another example, one that's a little more complicated.